I've been talking about the pseudo theorems, so I can briefly write them again, and then we have done some applications of them, and then we still need to prove them. So, pseudo theorems. I don't know, it's not the usual chalk. It's a very bad chalk. You know, it's very hard to write, and then it's almost impossible to take off. But anyway. So we have a G is a finite group. With number of elements is say p to the r. How do I want to write it? P to the m times r elements, and then we had to define the p pseudo subgroup is a subgroup H in G with p to the m elements, where obviously p does not divide R. Okay, and then so the first pseudo theorem that is that such a subgroup always exists. So a subgroup of number where the number of elements is the highest power of a prime p, which divides the number of elements in G. So the first pseudo theorem is that p pseudo subgroups always exist. Yeah, well, I'm sorry, I think I will get my own chalk. Have some reasonable chalk in my room. Okay, so this is the first one. The second one was that all p pseudo subgroups are conjugated. So it means if I have two pseudo subgroups H and H prime, then H prime is equal to G to the minus 1 for some G in G. And the third statement was some estimate about how many there are. Namely, if again I have that the number of elements of G is p to the n times r, the p is a prime, and it does not divide r, then the number of p0 subgroups I hope it's right, divides R and is congruent to 1 modulo P. Okay, so that means if I divide it. Okay, so these are the statements, and I think I missed, there was still one application I haven't done yet. So as I mentioned the other time, obviously if you have a group which is conjugated to a P0 subgroup, it's itself a P0 subgroup. So if you, for instance, see here that a group, no, if you can deduce from this that the group contains only one P0 subgroup, it automatically has to be a normal subgroup. And so we want to make a small application of this, which is the following proposition. It's a very simple application, so that G be a group such that of order P times Q, where P and Q are primes, and we want that, say, one of them must be larger, P is bigger than 2, so there are two different primes, and Q does not divide P minus 1, then it follows G is cyclic. Okay, so that means it's isomorphic to the PQ. So this is one very simple application of these zero theorems. So want to basically use what I just said. So so we write NP equal to the number of P0 subgroups. So what can we say? Then we know that P is congruent to 1 mod Q by the third zero theorem that I just had, and NP divides Q. What?
1 modulo P, not Q. No?
Yeah, that's what I meant. Obviously, yeah, that's what I wrote up there, so it also should be here. Also, it would be difficult to achieve, well, it would be possible, but anyway. So what does it mean? You know, as P is bigger than Q, it is not possible that NP is congruent 1 modulo P and still divides Q unless NP is equal to 1. Okay, so therefore we know that there is a unique P0 subgroup. So let H and G unique P0 subgroup. And which is therefore a normal subgroup. Of G. As we have just seen. Now let's play it with the other. So look at the number of Q zero subgroups. So let in Q be the number of Q zero subgroups. Then, in the same way as above, we have that in Q is congruent to 1 mod Q and NQ divides P. So if NQ divides P, it follows that NQ is equal to 1 or NQ is equal to P, because P is primary. But if NQ is equal to P, then P is congruent to 1 mod Q, which means that Q divides P minus 1. Then Q divides P minus 1, because NQ is supposed to be congruent 1 Q, which means that. So, which contradicts our assumption. So it follows also that NQ is equal to 1. And so, therefore, we have a unique Q zero subgroup. Which is again a normal subgroup. Of G. And so, well, now we are in the situation of the result of our little proposition before. So we have H and K are normal subgroups. And they are both cyclic of order P, respectively Q. So it follows that if I take the intersection, this consists only of a neutral element, because every element in H has order divisible by P. Everyone in here has order divisible by Q, and so therefore this only intersects if the order is 1. So if you have the unit element, and so on the other hand, obviously we have that the number. If I take the number of elements of H times the number of elements of K, this is P times Q. So by our proposition, we have that G is equal to the product, isomorphic to the product of H and K, which is isomorphic to ZP times ZQ, and we had seen that this is isomorphic to ZQ. So this was a very straightforward application of the zero theorems, because we have arranged it precisely in such a way that for obvious reasons there's one P zero subgroup and one Q zero subgroup. Obviously, if one wants to use the zero subgroup, the zero theorem to classify more complicated groups with the numbers of elements which have more prime divisors, it will be more complicated. One will have to have some additional ideas, but at least this gives you some hint. And just to see that, obviously this applies quite often. So, in particular, if we have, say, if the number of elements G is like 5.3 or 7 times 5, 11 times 3, and so on. So in many cases, we are in this situation, and we get that the group is cyclic. So we now know, we can precisely know up to isomorphism all the groups of, if the number of elements of the group is a prime number, if it's the square of a prime number, or if it's a product of two primes, which, you know, two different primes with this condition. Okay, so maybe in the exercise I will maybe have some slightly more complicated applications. So now I think we should try to prove the single theorems. So I want to prove this using something about actions of groups, and in fact I want to analyze some action of the group of its, you know, so given an action of the group on itself, I want to look at the action on the group on its set of subsets. So let's just make a little preparation on this. So on actions of the group on its subsets, so on the set of its subsets. So it's just, so first, it's an obvious remark. So if a group acts on a set, it also acts on the set of subsets of the set. So let G act on a finite, say for this case, finite set S, then G acts on the set of subsets by the obvious thing, by G comma U is mapped to GU, which is just the set of all GU with U and U. And you can easily see that this defines an action. No, the identity element will send a set to itself, and if you have the product of two elements, it will compose in the natural way. So this is an action, and one should also note, so as the map, so multiplication by G from U to GU is by definition always a bijection. No? It's a one-to-one map, so a bijection onto its image. It means that always U has the same number of elements of GU, so I can also view it as an action of G on the set of subsets of S with a certain fixed number of elements. Okay, so that's clear. So now, in particular, we now want to look at the situation where the set S is the group itself. And we will study two cases of action. One, the left translation of the group on itself, and the conjugation. So, let's see. I should also at least introduce one more word, namely, so in the situation here, the stabilizer of a subset U is a GU. So this is supposed to be the set, the thing which, such that u is sent to u under this action. So what does that mean? This is the set of all g and g, such that gu is equal to u, and as the action of g is a bijection, it is the same as saying that this is the set of all g and g, such that gu is an element of u for all u and u. Okay, that's the stabilizer. So it's not that every element of u is sent to itself, but every element of u is sent to a possibly different element of u. This is the stabilizer for this action on sets. And we have first a very trivial, I call it proposition, but it's more a remark. We can ask ourselves, what is the stabilizer of a set u? The whole group. So when, in some sense, is u fixed under the action, and so let g act on the finite set S, and u subset of S, then the stabilizer of u is the whole of g, if and only if u is a union of orbits. Of the action of g on S. That is actually almost by definition, because if you have an orbit, then the elements of g send the elements in the orbit to other elements in the orbit. So, so u is equal to g if and only if gu is an element in u for all u and u, and for all g and g. That's just the definition, and that's the same as saying so that gu is in u for all g and g means that the orbit of u runs there. That means that the orbit of u is contained in u for all u in u. And this is the same as saying that u is a union of orbits. No, it's just the union of all the gu for all elements in u. Okay, so there's nothing there, but we will use it. And now we want to, as I said, specialize to the case that our group, that our set S is the group G, and for the first we will look at the action by left translation. So that proposition. Let G act on G by left translation. So that means G, H, so the action of G on H is just by multiplication. So if I take any subset of G, then the statement is that the number of elements in the stabilizer of it will divide the number of elements in U. So then number of elements in GU divides number of elements in U. Again, this is okay. We'll see that this comes handy in a moment, but by itself, it's for this action, it's kind of a triviality. So we take, so let's say H be the stabilizer. So if you apply this result, then now we apply this result to the action of H on G by left translation. Apply the position to action of H on G by left translation. Okay, special case. And then what do we get? So in this case, the whole group is the stabilizer. So that means that that U is a union of orbits. But we know that for the left translation, this kind of map is injective. So every orbit contains as many elements. So every orbit of the action contains as many elements of H. Because with the multiplication, you have you can multiply and you can multiply by the inverse. It's a bijective map. So that means but for left translation, every H orbit has H elements. Oh, so there's no, with the left translation, there's nothing which is fixed. And so thus, if you use a union of H orbits, every orbit has number of elements H, it follows that the number of elements in U is divided by the number of elements in H, which is GU. Okay, so this was too simple. And now we want to make some simple remarks about the action of the group G on itself by conjugation and therefore on the set of its subgroups. So now look at action of G on its subgroups by conjugation. So if G is a group and H is a subgroup, then we can conjugate with an element in G. So for G in G, the conjugate subgroup, as we know, is G H G to the minus 1, which is just a usual thing. And this is a subgroup. And again, obviously, this is an action of the group G on itself. So this gives me an action on first the subsets of G, but as it sends subgroups to subgroups, it's an action of G on the set of the subgroups of G. So it gives action of G on set of subgroups of G. So here, just about this, we want to make a few simple remarks. So first, what is the stabilizer? I think you already should know what the stabilizer is. The stabilizer of a subgroup H is the normalizer n of H and we had that this was the set of all G and G such that G, H, G to the minus 1 is equal to H. Okay, it's the same as saying that. Okay, this was the normalizer, and this is, by definition, this is the stabilizer for this action. And we see that this is. We have already seen that n of H is a subgroup of G, and H is a subgroup of n of H, because every element of n of H obviously does this. Actually, H is even a normal subgroup of n of H, because this precisely says that for all elements in n of H, we have this relation which makes it a normal subgroup of n of H. In fact, n of H is the largest subgroup of G, such that H is a normal subgroup of it. But at the moment we don't need that. So therefore, we can make the following remark. So because of this, in particular, the number of elements in H divides the number of elements in NH and the number of elements in NH. So the order of NH divides order of G. So this is clear. And if we look at C, if we take C to be the number of different conjugate subgroups of H in G. So how many different subgroups can we get by conjugating G? Then we know, then we can apply the orbit stabilizer theorem, because the obviously the conjugate subgroups, so note that this is the orbit of H under this conjugation. So therefore, by the orbit stabilizer theorem, it's what? So the number of elements in the orbit, so if I take the number of elements in G, so the order of G is equal to the number of elements in the stabilizer of H, which is the order of NH, times this number of conjugate subgroups. Okay, so these are just, this directly follows. These are the simple facts that we are going to use. Now we want to start with the actual proof of the pseudo theorems. So for the first pseudo theorem, we will use this result about that we had about the action by left translation. But first we have a little lemma, which is just combinatorial, whatever. So if S be a set of p to the m times r elements, where as before p is a prime number and r is such that p does not divide r, the same assumption as before. So one could think of S as our group G. The number of subsets of S with p to the m elements, well, that standard is this number, the binomial coefficient. So that's standard combinatorial fact that the binomial coefficient tells you the number of subsets of as many elements, and I write it out because we're going to use it. I wanted to keep track of an average term, so maybe I call this n minus k, and then it goes on until n minus p to the m plus 1, and here p to the m minus 1, and it goes on, we have p to the m minus k, and then this. Okay, so this is this number, but this is kind of just standard. But what I want to say is the NP does not divide. Okay, and that's a simple fact. So first, as I said, this is standard. I assume you know that the number of subsets of choosing, in English you often just says this is p to the m choose n, so you choose p to the m out of n. That's precisely what you're doing. And so the only thing is that p does not divide n, and for that we have to just look what this is. So to see that p does not divide n, you just have to see that whenever some power of p divides the numerator, precisely the same power of p will divide the term directly below it. So we want to see, note that whenever say p to the l divides n minus k, which is some random factor in the numerator, also p to the l divides p to the m minus k. And in fact, if this is the highest power that divides, this will also be the highest power, and so p does not divide the whole thing, because every factor contains the same power of p as the maximum. And so just we write, to see this, we write k equal to say p to the l times s, where p does not divide s. Then clearly L is smaller than M, because this P was the highest possible power that divides it. And clearly also, and therefore, p to the l also divides p to the m minus k, which is because both are divisible, because this is also k is divisible by this. So when p to l divides this, as this is divisible by p to the m, it also has to divide k, and so we have this. Okay, and so in each factor here, the maximum amount of p that divides it is the same. And so altogether, we have even shown that one thing is, we already know before that it's an integer, but we have shown that at least p is not a denominator, and we have also shown that it's not divisible by p. Okay, so this is this little lemma, and now we want to prove the first zero theorem. I should say there are many different proofs of the first zero theorem. This one has the advantage of being quite short. It has a disadvantage, it's quite unexplicit. So we somehow construct this. You have to show that that the group contains a p0 subgroup, so a group with p to the m elements, and we will show that without telling you what in any explicit way what this group is. There are other proofs which make it more explicit, but the proof is then more complicated. So let S just the set of all subsets M in G, where so subset which has p to the m elements. Oh. So this set is here. So we decompose S into orbits under left multiplication. No, by G. So the action of, on subsets induced by left multiplication. So G times M is G comma M is sent to G times M. No, just this. So now we have this number N is the number of these subsets with as many elements, which is the number of elements in S. So therefore we have that N is the number of elements in S, so N from the lemma, which is, now we have divided into orbits, so it's the sum over all the orbits, which I call O, say, of G and S, and the number of elements in O. It's decomposed into orbits, so the total number of elements is the sum of the number of elements in all the orbits. So we know that P does not divide this number N. So we know that there must be an orbit for which the number of elements in the orbit is not divisible by P. There's an orbit so called O equal to G of some subset M such that P does not divide. The number of elements in this orbit. Okay. And now, what comes now? Well, we ask ourselves, what is the stabilizer of this group M? It will turn out that for stupid reasons, this has to be a p-stilo subgroup. So by the orbit stabilizer theorem, we have that the number of, so this p to the mr, which is the number of elements in G, this is equal to the number of elements in the stabilizer of M times the number of elements in the orbit. But G of M is not divisible by P. I forgot something. Yeah. There's one more thing, which I should have said earlier, but then we just see. So, by, it's not really working. So by the proposition we had before, we had that for the left translation, the number of elements in the stabilizer will divide the number of elements in the set. So by the proposition before, we have that Gm is a divisor of p to the r. So we have
P to the M.
p to the, yeah, the number was m. Yeah, I occasionally forget that. So this is, so we have that this number is divisor of p to the m. This number is not divisible by p, but this whole thing is divisible by p to the m. So the only way how this can happen is, so because of this, the number of elements here must be divisible by p to the m, and because of this thing, it cannot be more than p to the m, so it is p to the m. So thus, number of elements in Gm is p to the m. So it's a p-stilo subgroup. Yeah, so it's a rather short proof. The only thing is that, maybe you still don't really know, what are the elements in this thing. You have somehow, there is one orbit such that, and then you take the stabilizer of that. So that's not very explicit. But okay, there are other proofs where it's more explicit, and you have to work a bit harder if you really need to know what this thing is. Okay, so this was the first pseudo theorem. Now let's look at the second. Now, obviously, as we are talking about, that all pseudo subgroups are conjugated to each other, this must have something to do with action by conjugation. Or at least, let's see. Where do we have it? Yeah. So now we look at the proof of the second pseudo theorem. So we take two pseudo subgroups. G, and we have to show that they are conjugated. So to show there exists an element A in G such that H prime is equal to A H A to the minus 1. And so that doesn't seem to be completely easy because somehow we have to find this element. In the moment it doesn't seem to be anywhere. So now we do this now by letting, so we look at H prime acting on G mod H by just multiplication. So H prime acts on G mod H. So just a set of cosets by H prime of applied to a subset BH is just supposed to be H prime B H. So just by left multiplication on the cosets. Okay, we can do that. This gives me obviously an action. And as we do again something similar about something being prime to P and so on. Because we know as H is a P0 subgroup, the number of cosets is equal to R, which is prime to P. We have that this is equal to R, which is prime to P. So therefore, if we expect, as before, there must be an orbit such that the number of elements in the orbit is prime to P. No, because the number of elements here is the sum of the number of elements of all the orbits of the action. And so if this number is prime to P, then at least one of the orbits must have number of elements prime to P. So thus there exists at least one orbit, one H prime orbit, and I write this H prime of AH, where this will turn out to be the A you want, such that the number of elements is prime to P. And such that number of elements H prime AH is not divisible by P. Okay, and then we, I think, apply again the orbit stabilizer theorem for this action of H prime on this thing. So by the orbit stabilizer theorem, we have that the number of elements in H prime, which is what acts, which we know is P to the M, is equal to the number of elements in the stabilizer of the action of H prime on AH times the number of elements in the orbit. So we know that this number is not divisible by P. On the other hand, it's the divisor of P to the M, so it follows that this number is 1. So that means that the whole of this actually means that the whole of H prime stabilizes AH. So thus for all H prime, in H prime we have that H prime, or if you want AH is equal to AH, that means if I bring it to the other side, we have that H prime is an element in AH, e to the minus 1. No, I just, but I can also make it slower, so I have that H prime AH, so for all H in H, we have that H prime AH is an element in AH. And now we can multiply first with this from the other side and with this on the side, it follows that H prime is an element in AH, A to the minus 1. So that means, so in other words, we have shown that H prime is contained in AH, A to the minus 1. So it's contained in the conjugate subgroup of H, but obviously both of them have the same number of elements, and so they So, in some sense, it's a somewhat similar idea to before. You somehow force an orbit which has only one element, and then you can work with a stabilizer, and you find that that this will provide you with this. Okay. Now, finally, we come to the third Stabilizer theorem. Here we then actually use finally the conjugation action. So there were two statements in the first Stabilizer theorem. Something is it's divisible by, so the number of p zero subgroups will be divisible by R, and it's congruent 1 mod p. The first statement is kind of trivial, and the second one requires a bit of work. The proof of third theorem. So we know by the second Stabilizer theorem all zero p groups are conjugate. So that means the set of p0 subgroups is an orbit of one p0 subgroup under the conjugation action. So that is the number of p0 subgroups, or just whatever, the number of p0 subgroups is equal to the number of elements in an orbit of one p0 subgroup. We call H under conjugation. So now, by the orbit under conjugation with elements in G. Now, by the on orbit stabilizer theorem, we have that the number of elements in the orbit is equal to the index of the stabilizer in the group. The stabilizer is NH. So it follows by the orbit stabilizer theorem we have that this is equal to the index of NH in G. Since we know that H is a subgroup of NH, so since H is a subgroup of NH, we have that this thing, the index of NH here, divides the index of G, of H in G. So it's just, this is the quotient is the index of H in NH, which is R. And this is was the first statement. So there's nothing really here, we just use the orbit stabilizer theorem to this action and look at it. So now, the other statement that is congruent to one mod, the number of elements is congruent to 1 T is a bit more subtle. Not much, but a little bit more, so we have to. So let say maybe I call this number S, small s. So now show S is congruent to 1 mod P. So let's just look at the set of all P0 subgroups, just write them down. So we have some such groups. We know there are now S of them, so we have H1, H2 until HS. We will eventually want to know what S is, and we pick one of them and call it H. And we know, for instance, this is this H, so everything is obtained from this by conjugation. Obviously, you could take any of them, would be the same. So these are the P0 subgroups. Of G. And we now again decompose it into orbits, but this time under the conjugation action. Under the action of conjugation, and obviously not of the whole group because it's the orbit. This is one orbit of the action of the group on the subgroups, but we take the orbits under conjugation by H of action of H by conjugation. So it's kind of clear that if we look at the orbit of H under conjugation by elements of H, that's just one element, maybe H itself. Nothing happens if we conjugate it with itself. But the claim is that this is the only time when this is when the number of elements in the orbit is not divisible by P. So let's see. So in orbit, H of Hi consists of a single element if and only if every element in H does nothing. And we know that the stabilizer in G of this thing is the normalizer. So that means if H is contained in the normalizer of HR, if and only if H is contained in N of HR. So this has, note that H has still P to the M element, and HI has also P to the M elements, and the number of elements in N of HI is a divisor of the number of elements in the group. So that means both H and HI are P pseudo subgroups of N of HI. And furthermore, one of them is a normal subgroup, because we know that HI is a normal subgroup of N of HI. And HI is a normal subgroup. But we know that any two P pseudo subgroups are related by conjugation. So if you have two P pseudo subgroups and one of them is a normal subgroup, then it means there's only one P pseudo subgroup which is equal to this. So thus H is equal to HI. So we have shown that the only kind of P pseudo subgroup for which the orbit consists of a single element is H itself. Okay? So thus H1 equals H is the only P pseudo subgroup. Whose each orbit consists of one element. But we know, now if we take any other orbit, we know by the orbit stabilizer theorem we have that the number of elements in H is equal, so for I different from 1, by the orbit stabilizer theorem, we have the number of elements in H is equal to the number of elements in the orbit times the number of elements in the stabilizer. Now, this is, again, P to the M. So we know that this number is not 1, so it must be a divisor of P to the M which is not 1, so it is divisible by P. And so, if I, the number of elements in every orbit is divisible by P except for one orbit in which there's only one element. So therefore, the number of elements, the number of elements in S altogether is congruent to 1 not P, because one summand is 1 and all the other ones are divisible by P. Okay. So maybe we can have out. So this is the sum of all orbits, the number of the elements in the orbit is going to 1. Okay, so this was the third zero theorem. Okay, so that was as much as I for now want to say about groups. I will also give you some homeworks about this. Try to do it today. I haven't. So this now obviously there's much more one can say about groups, but you know, that's as much as I wanted to say here. And now we start a new topic, which is first rings, which is mostly rather elementary. We start again at 0, and maybe you find it a bit boring, many new words, and we introduce them and do kind of obvious things with them, as we did with the groups. So in some sense, the only somewhat more subtle thing were these zero theorems. But now we start again from scratch, and then after that we'll come to fields and Algebra theory, which is again a bit more difficult. So let's talk about rings. Just on some basic language. So, I mean, it's clear, in a group we have one operation, which usually denoted as multiplication, and there are some actions for that. In the ring we have two different operations, which are viewed as addition and multiplication, where we, and somehow the simplest example of a ring, which is that one thinks of as usually the integers, and you want to kind of generalize some properties of those. So let me give the proper definition. And then, okay. So a ring is a non-empty set. With two binary operations. Which I note as addition and multiplication. And for the addition, we assume that it makes R into an abelian group. So R with addition is an abelian group. And for the multiplication, we assume in the moment much less. We just assume that the multiplication is associative. And as basic compatibility between the two, we assume the distributive law. So multiplication is associative. And we have the distributive laws. So if we take A times B plus C, this is A times B plus A times C. As before, we're allowed to drop the multiplication sign, and we also B plus C times A is equal to BA plus C. So for all A to C. So this is just this basic thing. And in particular, this is an abelian group. We call gamma plus is called the additive group. Of R. So in the moment we make very few assumptions on the multiplication. So, as I said, one example is the integers with addition and multiplication are a ring. But it has also some other nice properties. But let's, I want to, it's not very important, it's a trivial formulation. This distributive law we can reformulate in a rather obvious way, namely, remark, if we look at the, so reformulation of distributive laws, if we take, so for all A in R, if we take the left multiplication by A from R to R, which sends P to AB, or if we take the right multiplication from R to R, which sends P to BA, these are group homomorphisms for R plus. And this is just what's written. No, that's just the other formula. So if you have a group, you then want to look at the corresponding sub-object, so a subgroup. And the subgroup is just the subset, which so for a ring, it's just a subset which with the induced addition and multiplication is a ring. So definition, the subring A in R is a ring, is a subset such that first A with the addition is a subgroup of R with addition, and we just want that it's closed under multiplication because we have not any further assumptions. So for all AB in A we have A times B is it. And obviously then A becomes itself a ring with the induced addition and multiplication. And of course an example, so for instance 2 times Z is the subgroup of Z. Okay, because it's clear that we know it's a subgroup for the addition, and then if two numbers are divisible by a certain number, then the product is also divisible by that number. These are all sometimes, often, group rings can have nicer properties. So somehow for the addition we have already all assumed everything we possibly might want. It's in a Lie group. But for the multiplication you can impose other nicer properties. For instance, you could assume it's commutative. And you say the ring is commutative if the multiplication is commutative, because the addition already is, so it's not a condition. And some other such properties. So definition. Ring R is commutative if whatever just has AB is equal to BA or AB in R, which means that the multiplication is commutative. And we also have, so we have assumed that the addition is a group, so we also have a neutral element for, and so we could also assume we have one extra assumption we can make, that we have a neutral element for multiplication. So an element which I denote R. So it was not precisely so when I didn't write it carefully on the blackboard. Obviously, if you so in the assumption, when I say that the additive group R plus is a ring, is an abelian group, then this also means it has a neutral element, and this neutral element we call 0. It's a distinguished element of the ring. I don't think I wrote that. So an element which I call 1, and I assume it's different from 0, so from the neutral element in multiplication, is called a unit element. If it's a neutral element for multiplication, so if A times 1 is equal to 1 times A is equal to A for all elements R, and it's easy to see that then 1 will be unique. Determines it. If a ring contains such a unit element, it's called a unital ring, or sometimes also just say a ring with 1. So if R contains a unit element, it is called a ring with 1, or a unital ring. So this thing is called unit element. There's also the word unit, which we'll introduce in a moment, which is something slightly different, so one has to distinguish it. So mostly in future we will study commutative rings with 1, commutative unital rings, because we are more interested in those. We just give a few examples of rings, from obvious to slightly less obvious. So if we take standard examples, Z, Q, so the rational numbers, R and C are all commutative rings with 1. We'll see there also more. Examples, then we can look at the so-called ring of Gaussian integers, so Zi. So I assume you know what the complex numbers are. So this would be set of all n plus ni in the complex numbers, where I is the imaginary unit, where n and m are integers. And you can see that, and then multiplication is the multiplication in the complex numbers, so I squared is equal to -1. And this is contained in the complex numbers, and it's a subring of the complex numbers. This is called the ring of Gaussian integers. Then let's look at the non-commutative example. For instance, if we take the 2 by 2 matrices with coefficients in R as an example. So this, as you know, we have just these matrices. In the numbers, say, then this is a ring with matrix addition. So you add them. You add the same components and matrix multiplication, which you know from linear algebra. And you also know that this is not commuted. Now we can easily find some elements which don't commute. We look at another example. So let G be a finite group. So now I look at the group ring. Of G is, I denoted ZG. This is just a set of all formal expression like this, sum G in G, NG times G, where NG is in Z. So let me explain the notation. So what this just means, so I assume it's a finite group, so it just is a vector. If G has n elements, it's just a vector of n elements, which I label by the elements in the group, but I write it like this to explain how I want to work with it. And what is the operation? So the addition is just component-wise, so add the same things. So addition, sum G in G, and G times G, plus the sum G in G, mg times G. This is just take the sum. So that's trivial, but to get an interesting multiplication, we use the group structure of the group to define the multiplication. So multiplication is, so if I take sum G and G, I first look up G times G times sum G and G, mg times G. Well, how do I want to do it? I want to say that I multiply the elements in the group and their coefficients and sum everything up, and formally impose that the distributive law holds for all this. And so what does this mean? This is first, if I might just formally multiply it out, I get the sum over all pairs G1, G2 in G of n G1, m G2, G1 times G2, but this is the multiplication in the group. And then but I'm supposed to write in this form, so I have to collect terms so that it's in this form. This is the sum over all G and G, the sum over all pairs G1, G2, just that G1 times G2 is equal to G n G1 times m G2. So this is the coefficient times G. So you can easily check that this defines a ring, because basically the way I wrote it here, I have precisely imposed the distributive law. And so basically what I have said is we want that n g1 times m g2, we want this to be n m g1 g2, and then for this notation here with the sum, the distributive law should hold. This is the definition.
And this G is equivalent class, or?
No, G, no, I mean, I could also have just written G if you want. It's not equivalence class, it's just a formal symbol which tells me that this depends on G. No, it's just, what it really is, if you think of it in other forms, you just have a tuple n1 to n g. No, that's just a different way of writing the same. I just say I have somehow ordered, I can write it like this, or here I write this bracket to just remind us that we are not really multiplying an element in G, but it just is a placeholder which tells me that it corresponds to G. But it's not an equivalence class, it's just there are as many components here as there are elements in G. Okay, so this is also, you can easily see this will be a ring. If G is not commutative, this will not be commutative. And you can also do it with other coefficients instead of the integers, for instance with the complex numbers. And this group ring plays a big role also in representation theory, so it's a certain way how you understand in other terms what happens in the group.
To connect between the two views of this element, the first line, here G is a tuple all zeros and one on the G's position, right?
Yeah. That if I want to write it like this thing here would be, all the coefficients are 0 except the one corresponding to this G1. No? That's what this is the short form for this. Yeah. Okay. Then maybe I've used enough of your time. So we will, I think, meet on next Friday, because we meet on Friday, tomorrow, and then after that we meet next Friday, because next week I have some school where I also have to teach some course and stuff. Okay, so anyway, see you tomorrow. Now,